Okay, so techniques of integration start to come into play, and this is what Chapter 7 really is all about. These techniques become so important, and so 7.2, what we're going to do is we're going to start to attack problems by using trigonometric integrals. And so I wanted to start off with a problem where we can use methods that we already know. And so with this problem here, the integral of cosine cubed, what we can do is we can try to break this problem up into a way that might be able to help us solve it. And so we have to get a little bit creative. And so here's how we're going to do it. So I'm going to rewrite this problem to be the integral of cosine squared x times cosine of x dx. And then I'm going to remember my identities. Okay, the identities are important here. And I know that cosine squared is the same as 1 minus sine squared x times cosine of x dx. And now I'm going to use a method that we learned in Calc 1, which is using a u substitution. And so my u in this case is going to be sine of x, just because it's got the power on it. That's why I'm using the sine of x. And so when I take the derivative of this, I'm going to get du is equal to cosine x dx. And we notice that cosine x dx takes care of this. So this whole thing right here will become my du. And so what I'm going to have is I'm going to go 1 minus u squared du. And we can see this is du, right? And then the sine squared piece, or the sine, is u, so now it's going to become u squared. Well, we can take the integral of this, right? So the integral of 1 is u, and the integral of u squared is u to the third over 3. And then we need to add a constant c because we have an indeterminate integral. Is this coming back to you guys? Are you remembering this?
Yeah.
Okay. Then from here, in order to get our actual answer, we need to substitute back into what our u was, and so we end up with sine of x minus sine cubed of x over 3 plus some constant c for the indeterminate value. And there is our first problem. Okay, so it is manipulation, correct? We're trying to manipulate in order to be able to solve these problems. And that one was just, it was cosine, so then we had to break it up in order to be able to attack it. Are there any questions on how I did this? No? Okay. All right, so then let me continue. And this next problem then, we have powers on both, right? And so in the previous one I said, oh, it's a u substitution. We can see the one that has the exponent, and so that's why we did the u in this part right here. This had the exponent, so that's why we had the u. But in this next one, we end up having an issue, right? Because they both have exponents. So what we're going to have to do is be creative in how we decide to break this up. And so there's a method to it, but before I talk about that method, I'm going to demonstrate what I'm doing and then introduce the method. So what I'm going to do is I'm going to take this and go, okay, sine squared of x, because that's an identity, squared.
Sorry to interrupt, Professor. Are you recording this?
Yes, it's being recorded.
Okay, sorry, thank you.
Yeah. So sine squared of x, because it's an identity, squared times sine of x, right? Times cosine of x dx is how I'm going to break this up. Okay? Now the sine squared, I can use the identity on, and so what I'm going to get is 1 minus cosine squared of x squared. You agree that that is still sine squared, correct? sine of x, and in fact I'm going to write this in a way that you guys can see it. I'll go cosine of x, sine of x dx. You agree with that, right? All I did was switch my sine and cosine. A times b is equal to b times a. And then from here now I can do a u substitution. So the u substitution that I'm going to do here is I'm going to say u is cosine of x, because it has the exponent. And so I'm going to get du is equal to negative sine of x dx. And we can see that we have sine of x dx, but we don't have the negative. So what that tells us then is we have to bring the negative out front. So I'm going to get a negative. Emiliano, do you have a question?
Yeah, I think you forgot to include it's supposed to be cosine squared x.
Oh, squared. Perfect. Thank you so much. Appreciate that. Okay. It doesn't affect the problem in terms of where I'm at, but yes, thank you. So then I'm going to get the minus from here, and then I'm going to go 1 minus u squared, u squared, and then this will become du. Do we agree?
Yes.
Okay. So then from here we're going to expand, because we should expand, and I'm going to get 1 minus 2u squared plus u to the 4th times u squared du, and then distributing in, I'm going to get u squared minus 2u to the 4th plus u to the 6th du. And then when we integrate here, I'm going to get negative u to the 3rd over 3 minus 2/5 u to the 5th plus u to the 7th over 7 plus some constant. Ooh, I didn't change my signs. That should be a positive, that should be a negative, plus some constant c. People often get these problems wrong because they stop here. Remember that you must bring it back to the u that you originally had. So in this case, our u is cosine, so we're going to get a minus cosine cubed x over 3 plus 2/5 cosine to the 5th x minus cosine to the 7th x over 6 plus some constant c. And you can make those fractions in front if you preferred. It doesn't really matter to me. So that could have been 1/6 and 1/3 in front, but that's the gist of this problem. Are we okay with that?
Yeah.
Okay, cool. Okay. Now this problem here introduces something that's going to complicate things a little bit for you. When we have something that's in terms of sine squared or cosine squared, we have to use something called power reduction. And this is something that's going to be new, but very, very useful. And so let me just write that down so you guys have it. So whenever you have cosine squared or sine squared, we want to attack it with power reduction. And here's how the power reduction works. If I have cosine squared x, the power reduction tells me to go 1/2 1 plus cosine of 2x. Those are equivalent. So 1/2 1 plus cosine 2x is equal to cosine squared. Sine squared x is equal to 1/2 1 minus cosine 2x. Are we okay with that?
Yes.
Okay, so these are just rules that you'll have to know and be able to process. All right. Now, in the problem that I'm giving you, it's a definite integral, so we won't have the plus c, but we will have to use power reduction because we can see that we have sine squared, right? So sine squared is going to be 1/2 1 minus cosine of 2x dx, and our bounds stay the same. Then we can break that up to be 0 to pi of 1/2 dx minus 1/2 0 to pi of cosine 2x dx. So this will be 1/2 x evaluated from 0 to pi minus 1/4 sine of 2x evaluated from 0 to pi. There might be a question there. I can come back to that in just a second. And then when we evaluate, I'm going to get 1/2 pi minus sine of 2 pi is 0. So that's going to be 0. And then with the zeros, we're going to get 0. So our answer ends up being 1/2 pi. Now, I'm sure you might have a question about how I went from here to here. Am I right?
Yep.
Okay, so in order to be able to do that problem, what's going to end up happening is we're going to let u equal 2x. So then du is going to be 2dx. So that means 1/2 du is my dx. So when I come back to that problem, I have 1/2 with a 1/2 in front, so I have to multiply by that, integral of cosine of u du. So that gives me that 1/4. The integral of cosine of u is sine of u, correct? But u is 2x, so I get 1/4 sine of 2x. And that's how I got this piece right here. Are we okay with that? Yeah. Okay. The lift is coming. All right. I'm just going to give you guys some time to copy that and absorb that. Make sure you're okay before I move on, because I definitely don't want to overwhelm you, and I think there's a lot to today. And I won't see you till next Wednesday, so I want to make sure that you're able to absorb this. All right, am I good to go?
Yeah, I'm all done.
Okay, Emiliano, you have another question? Or do you need me to just clear that? That might have been from prior. I didn't clear it. Okay. Okay, let me go on to the next thing. Now, this again is a problem that is in that power being lifted. Unfortunately, in this case, I can't break it up to identities. It isn't helpful because I end up with sine squared squared. And when I break that up, there's nothing to do with u substitution with. So I have to attack this as a power reduction. And so when I attack it as a power reduction, it's 1/2 1 minus cosine 2x, but this whole thing is squared. And it's important that you guys notice that the whole thing is squared, because a lot of people forget to square the 1/2 and don't get the 1/4 that comes out of it, and then that messes up your whole answer. So it's imperative that you know that this whole thing inside this bracket is sine squared. Does that make sense?
Yes.
All right. Oh, I wish I could see your faces more so that I can make assessments. Okay, so then from here, what I'm going to end up having is 1/4 1 minus cosine 2x squared dx. So Wanting to clean that up, I'm going to take the 1/4 out, and I'm going to get the integral of 1 minus 2 cosine 2x plus cosine squared 2x, all of this times dx. Right? The expansion is okay? Okay. I'm going to break it up into 3 integrals so you guys can see what's happening. So I'm going to have 1/4 integral of dx minus 1/4, in fact, now, times 2 integral of cosine of 2x dx plus 1/4 integral of cosine squared 2x dx. The first two we can now do. This one's going to be 1/4 x minus this one's going to be a 1/2, but then a 2 is going to come out, so I'm going to get 1/4 sine of 2x. If you have a question about this one, it's the exact same process that I did on the one above. I made u2x and then did the substitution. But I'm willing to show the work if you guys need it. And then this last one I can't quite get. One of the things I should be kind of disciplined with, these are all indefinite integrals, so that's plus c1, that's plus c2. This one over here is then going to become 1/2 1 plus cosine 4x dx, correct? Because I have to do power reduction to it. And so I'm going to have 1/4 x minus 1/4 sine 2x, and then this will be plus 1/8 the integral of 1 plus cosine of 4x dx. And so this is going to become 1/4 x minus 1/4 sine of 2x plus 1/8 x plus how do I want to show this to you guys so you guys can see this. I want to be careful. That's good. I'm going to get sine of 4x, and then in front of it I should get, looks like I'm getting 1/32. I think that's wrong. I want to see why. The 1/4 across. Let me see if I can see what's going on there. I think this is right. U is a 1/4. That's going to come down 1/34. Yep, I think that's good. And then we can combine like terms. I should add one important thing, the plus c. And then we're going to get, this is a like term with this. So I'm going to get 3/8 x minus 1/4 sine of 2x plus 1/32 sine of 4x plus some constant c. Yep, that's right. Are we okay?
Yeah, that makes sense.
And then notice what happened is this constant plus what ended up being this constant and this constant combined to be one new constant. Because 4 unknown constants added up become a new unknown constant. I don't care what number they are, they're just an unknown constant.
So Mateo,
Yes.
for the 1/4 sine 2x, isn't it supposed to be 1/2 sine 2x?
Let me see.
Because at the point before you finished integrating, you have 1/4 times 2.
Oh, you're talking about right here. from here to here.
Yeah.
Okay, you're right. So what ends up happening here is when I take the integral of this, a half comes out. So the half cancels out the 2.
Oh yeah. Okay.
Does that make sense? So in this example here, and this is, you see this becomes a 1/8, correct?
Yeah.
But then I need to multiply that 1/8 by 4, because when I do a u substitution here, a 1/4 comes out. So the 1/8 and the 1/4 become the 1/32.
Okay. Got it.
We okay? Okay. Here are the rules to these problems. And obviously I'll print these notes out so you guys can absorb them. So what you're going to do is when cosine is an odd power, like I did in the example up above, I manipulated it so that what we end up having is everything's going to be written in terms of sine. So when you have sine and cosine's an odd, you break up the cosine so that everything can be written in terms of sine. And then your u becomes sine of x. Okay? If sine is the odd power, then you're going to manipulate sine to be broken up and write everything in terms of cosine, and then u is going to be your cosine, like they say right here. Okay? Now the interesting part is when they're both even, you do power reduction to both. Okay? And this is the power reduction that I was talking about with you guys. Does that make sense?
Yes.
Okay. So those are the manipulations that you're going to do these problems. This is going to take time. So please study this in the notes. I'm going to use them to be able to demonstrate things to you guys so that you're successful. Okay? All right. Okay. How are you guys feeling?
I get it so far.
All right, that's
I think I got the hang of it.
okay. Cool. I want to make sure about this problem. For some reason, it's bugging me. So that's right. That's 1/4. I think my math looks good, but it's bugging me. But okay, whatever. I'll come back to it. All right, now let's do another example. And this example is now when we have tangents and secants. Both are even. There is a strategy to this. So what I'm going to do is I'm going to manipulate this so that I can again be able to integrate. So in this example, what I'm going to do is I'm going to use my u to be tangent of x, because the derivative of tangent is what?
Secant squared x.
That's right, it's secant squared x. So since it's secant squared x, that's going to be something that's going to be helpful for us. Because then I can break this problem up to become, okay, let's see if we can clean this up. I'm going to go tan of 6x times secant squared of x times secant squared dx. And we can see now that from here, that secant squared dx is our du, right? Do you guys see that?
Yes.
Okay, so that becomes helpful. I also know that I can now manipulate this thing so that this is going to become u to the 6th, right? And I know that secant is a rule in terms of tangent, so it's 1 plus u squared du. And the reason I know that, and maybe I should write the step for you guys, just to be really cool. I'll have tangent to the 6th times 1 plus tangent squared x secant squared x dx. So then when I do the u, I'm going to get u to the 6th 1 plus u squared du. We okay with that? Then from there, distributing, I'm going to get u to the 6th plus u to the 8th du. So that's going to integrate to be u to the 7th over 7 plus u to the 9th over 9 plus some constant c. And then we need to substitute back in. So I'm going to get tangent to the 7th x over 7 plus tangent to the 9th x over 9 plus some constant c for our indeterminate. Are we okay?
Yeah.
Okay, so we can see when they're both even with tangent and secant, we want to try to manipulate to break up the secant so that our tangent can be the u. Okay? When they're both odd, well, make sure that everyone's written that down. Okay, can I move up?
Yep.
All right, just trying to make sure because I don't want to rush anybody. Yeah, this is going to take some practice. Luckily, you have a full week for this. So my advice is I didn't give you a ton of homework. I'm not going to do a ton of homework, but one thing I do want to recommend is that you guys spend some time looking at the book and seeing if you can do some of the examples that are in the book. Okay? Yeah, it's going to take practice. Okay, so now when we have odds, right, tangent to the 5th and secant to the 5th, I'm going to break up the secant again. So I'm going to have tangent to the 5th of x, secant to the 6th of x, and then secant x. Ooh, I'm going to actually break up both of them. My bad. Tangent x dx. And you should see something here. By me breaking it up this way, what do you think the u should be? Any guesses?
This is tangent again?
X tan x.
So it's funny, it actually should be secant. Because the derivative of secant is secant x tangent x. And then with the dx, this piece gets eliminated.
Okay.
So in this example, we're going to go u is secant of x, so that when I go du, I'm going to get secant x tangent x dx. So what do you think I want to do with tangent now? I'm going to want to write tangent in terms of secant because my u is secant, right? So I know that tangent is secant squared x minus 1, but that's got to be squared. I'm going to have secant to the 6th x, and then that's going to become secant x tangent x dx. Okay? So when I do the substitution, I'm going to get u squared minus 1 squared, u to the 6th du. We okay?
Yeah.
All right. So then from here, let's expand this thing. So I'm going to get u to the 4th minus 2u squared plus 1 times u to the 6th du. That's just expansion. And then I'm going to get u to the 10th minus 2u to the 8th plus u to the 6th du. which will yield u to the 11th over 11 minus 2u to the 9th over 9 plus u to the 7th over 7 plus some constant c. Agreed?
Agree.
So then this yields secant to the 11th x over 11 minus 2 secant to the 9th x over 9 plus secant to the 7th x over 7 plus some constant c. Are there any questions? Is there anything that's uncertain? We're okay?
It makes sense.
Okay. Some of you guys are like, maybe next week after I've watched this like 3 times. That's okay. Like, that's part of the reason why I'm glad that we're recording, so that you guys can see this more than just this one time. And if there's anything that you think I'm being unclear on, please speak up to that so I can be as clear and thorough as I can. Okay? Someone's going to say something?
Yeah, no, it all makes sense. It's just a lot to write down at one time.
Oh, no, for sure. Wait till you start doing the homework. Okay. Here is the rules to this. And it's just a breakdown, like I said. If secant is even, it's the one that you're going to want to break up and then use tangent. And then if tangent is odd, then you're going to want to use u as your secant. Okay? Don't worry about writing this down. You guys can print this off. I don't want you writing all of this stuff down. But those are the rules right there so that you know how to attack this. Okay? And then I tried to demonstrate one that was the even with the odd, and then the breakdown so you guys can see it. All right. Are there any questions? No? All right. Let me show you the next example. This is a problem I've done with my, I did this problem with my Calculus 1 class. So this should be a problem that you should be familiar with from Calc 1. In order to attack this trig problem, what should I do? Any thoughts? Perfect. Yeah, perfect. We want to break it down to be in terms of sine and cosine, right? So when we break it down to in terms of sine and cosine, I'm going to get sine of x over cosine of x dx. And from your Calc 1 class, here it's the u should be the denominator, correct? So our u in this case is going to be cosine of x. So we're going to get du is a negative sine of x dx. And so when we do the integral, I'm going to get negative 1 over u du. Are we okay? And then probably the way that your teacher talked about these problems is thinking of it in terms of the antiderivative, right? So what derivative gives you 1 over u?
Yeah,
What's that? I'm sorry?
natural log, ln.
It's the natural log, correct. So we're going to get the natural log of the absolute value of u plus some constant. Now we're going to substitute in. And then we have to remember some logarithmic rules. So when there's a coefficient in front of a log, that is an exponent of the term inside of the log, correct? So then what ends up happening here is I get ln of cosine of negative 1x plus c. And in fact, what I should write it so that you guys don't get confused, I should write it this way because then people will think it's arc and it's not arc. This tells me that that is in fact ln of 1 over cosine of x plus c, which is ln of secant of x plus c. I would actually accept this too. I'm fine with that. I'm not sure what WebAssign will do, but this one's cool and this one's cool for me. You okay?
Yeah.
Okay. Now some more trickery. With secant of x, there has to be a trick that's done with it. It's not one that is straightforward. So this is one I would suggest that you just memorize that's special. Okay? And the other one that's special is cosecant of x. That's knowing what the derivative of cosecant of x is to be able to manipulate it. So in this example here, what we're going to do is I want to generate something that can be substituted out, and so or u'd out. So what I'm going to do is I'm going to go secant of x, secant of x, and then I'm going to multiply that by secant of x plus tangent of x over secant of x plus tangent of x dx. And the reason that I'm doing this is because it makes this problem become very basic for me. I'm going to end up with secant squared x plus secant x tangent x all over secant x plus tangent x dx. Agreed? Okay. And then I told you guys, when we have problems like this, if we're going to do a use substitution, we usually use the denominator when it's a quotient, right? Since we can't really break this up. And so what I'm going to do is I'm going to say, okay, u is secant of x plus tangent of x. And when I take the derivative of that, the derivative of secant of x is secant x tangent x. And the derivative of tangent is secant squared x dx. What do we notice? The derivative is the numerator of our problem. So what ends up happening here is we end up with the integral of 1 over u du. Something that's very manageable for us, correct? We know then that's going to be ln of absolute value of u plus c. Then when we go to do the substitution, it's ln of secant x plus tangent x plus some constant c. But if you don't remember the process of multiplying both top and bottom by secant of x plus tangent of x, you're stuck. Okay? So this is one that's going to be important for you all to be able to process and memorize. It's just a special case. Okay, are we all right?
Just a quick question, Professor.
Yes, absolutely.
So like you're saying for the equation to evaluate secant x dx, so this is the only way, at least now that we're learning, to be able to solve
The strategy
this
for this
equation.
problem, this is it. Yes.
Okay.
Yeah. In fact, if I'm totally, I can't think of another way. So I think this is the only way, but don't quote me on that. I'm sure there's probably another way, but I can't think of one through my journey through math of doing it another way. Okay? So the trick in this one is multiply by secant x plus tangent x. When you do cosecant of x, I believe it's going to be cosecant x minus cosecant x cotangent x. I'll have to work that one out, and then I'll give it back to you guys. I'm just doing it off the top of my head, but I think that's correct. All right, have you guys written this one down?
Yep.
Okay. Typically, I put a problem like this problem embedded in an integral, so that I find out if you really do know the process to this problem. So it's never just, oh, what's the integral of secant of x? It's like it ends up being an integral that's broken up with the integral of secant of x embedded. So be prepared for that. Okay? How nice am I to tell you that? You guys are like, not that nice, you're putting it on the test. All right, so the next one. So now we have tangent cubed, and we don't want to attack tangent cubed with sine cubed over cosine cubed. I mean, we could, but that would suck. So we're going to attack this much like we attacked the first problem, which was what? I think it was cosine cubed was the first problem I did. So I'm going to break this up in that same format. So what I'm going to do is I'm going to take it and I'm going to go, all right, tan squared x times tan of x dx. And then I'm going to use the identity and go, all right, secant squared x minus 1 times tangent of x dx. And then from here, what I can do is I can break this up. So this is where this problem's a little bit different than the cosine problem. This one's going to become two integrals. So I'm going to end up with secant squared x tangent x dx minus the integral of tangent of x dx. Okay? And part of it is that now we see something, right? That second integral we've already done today. We know the answer to that one is ln of secant x, right? So it becomes this strategy like, okay, cool, I know this guy. I can show the work if he's going to put it on the test, but I don't need to show it if I'm just going to go get an answer because I know what it's going to be. That's going to be written as sine of x over cosine of x. I'm going to do use substitution. It's going to lead me down this thing to the answer, right? The other one isn't quite so simple. So what we're going to do is we need to be creative in our use substitution. So if I were to use secant kind of sucks because if I use secant, which it would have worked, and I can show it to you, you would have gotten secant squared, secant x tangent x, right? But an easier way to do it would be to use tangent because tangent is going to give me secant squared and eliminate it. So I end up with, dx, I end up with the integral of u du. And we know this one over here, I'm just going to leave it since we already did it. This will be u squared over 2 plus some constant, right, minus ln of secant x plus some constant. I'll just call it some constant. We said it was tangent, so that's tangent squared x over 2 minus ln of secant of x plus some constant c, and that's my answer. If I would have made it secant my u, my answer would have been secant squared x over 2 minus ln of secant of x plus c, and that would also be the right answer. So did I confuse you enough by doing that? Do you want me to demonstrate that for you guys?
Yeah, can you demonstrate that, please?
Yeah, no problem. Let me go all the way down. And our problem was secant squared x tangent x dx is our integral. So I'm going to break it up so it's secant of x, tangent of x. Agreed? So if I make u secant of x, du is going to be secant of x, tangent of x dx. So can you see that this goes away?
Yeah.
And now I end up with the integral of u du, which gives me u squared over 2 plus some constant c, which is secant squared x over 2 instead of tangent squared x over 2. The rest of the integral would have been the same, right? Minus ln of secant of x plus some constant c. So how we attack it, now we end up finding out that there's multiple possibilities for answers. Remember when your teachers used to always say, I love mathematics because there's only one answer? Do you remember that? Turns out that's not true. But there it is. And I just showed you, you can get multiple answers and they are both correct. Any questions?
So if we get a question like this on the test and there's multiple answers, and let's say, because I know WebAssign is really specific.
WebAssign will give
you
WebAssign will give you both of them correct.
Oh, okay. All right, good.
WebAssign will give you both of them correct, so don't worry about that. Yeah, that's a thing when grading these exams. You're looking at them going, oh God, dang it, this person did it this way. I made my key the other way. Dang it. And then now I have to do it the other way just to make sure that what they've done is correct. But that's the joy of this stuff, and it's cool. I'm trying to give you guys as many tools as possible to be successful. Are we okay with this problem then?
Yes.
Okay. All right, now to do secant cubed of x. Now the bummer part with secant cubed of x is we think, oh, maybe we can do some breaking it up like the tangent one, right? So it's like, okay, with the secant squared x, secant of x dx, is there anything that I can do to try to break this up? And a lot of people look at this and they go down the rabbit hole of, oh, secant squared is, what is it? I always mess that up. Is it minus? I think it's 1 minus, right? Tangent?
1 plus.
1 plus, whatever. I never memorize them. I always do this. Sine squared plus cosine squared x equals 1, and then I'm like, what do I want? Oh, I want tangent, so okay, divide by cosine squared. And then I'm like, oh, okay, so that's tangent, that's 1, that is secant. So that's how I've done it, right? I don't have a lot of space in my brain. I'm not that smart, so I just memorize one and then generate it from there. So if we go that way, we're going to get tangent squared x plus 1 times secant x. And I'm not telling you to write this down. Don't write this down. I'm just trying to demonstrate this. What can we do? Could I have gone, all right, tangent squared x, secant x plus secant x dx and try to attack this integral like that? We could. The problem here is we're going to end up with stuff that gets really ugly. So instead of attacking this problem like this, I'm going to attack it like a product and use what I taught you guys in 7.1. Okay? This would have worked, but it ends up getting really tedious. And I don't want to go down that rabbit hole, so I'm going to do an easier method. So from here, I'm going to use a new method that we learned, right? And that new method was a UV substitution, right? And so the UV substitution ends up being, wait, how do I decide what's my U? I'm going to use my U to be my lowest powered secant, and my dV is going to be secant squared x dx. And the reason that I'm doing this is because I know that the integral of secant squared dx is what? It's tangent x. It's something that's easy, where the integral of secant x is something that's going to bring me ln's, and I don't want to deal with ln's, right? That's going to get way more complicated, so I don't want to go down that way. So then from here, what I'm going to end up getting is this secant cubed x dx is going to be equal to u times v, which is going to be secant x tangent x minus the integral of v du. So the integral of v, which is tangent of x, times du, which is secant u secant u tangent x dx, right? Which will clean up to be secant x tangent x minus the integral of tangent squared x secant x. And isn't this the same thing that we had in the previous problem? Where it was, but it was just secant, and I had secant tangent squared. Wasn't that the same thing I had? So it ends up that we end up with something ugly anyways, but that's cool. At least we've done one part of the integral. So I'm going to get secant x tangent x, and now from here I'm going to use my trig identities, and so tangent is going to be secant squared x minus 1 times secant x dx. Agreed?
Yeah.
Which will then be secant x tangent x, and I'm going to break this up. Integral of secant cubed x dx minus, becomes a plus, the integral of secant x dx. But do we notice something strange here?
Do we have the integral again?
We have the actual integral that is our problem in our solution. So we need to be aware that this problem is called a looper. The integral itself is part of the answer, so we need to bring it to the other side, and we end up getting 2 integral of secant cubed x dx is equal to secant x tangent x plus, what's the integral of secant of x? Do you guys remember? We did it. Isn't it ln of secant x plus tangent x? Right? Plus some constant. Do you guys agree with that?
Yeah.
And then we need to divide by 2 because the problem that we have only wants the integral of secant cubed. So the integral of secant cubed x dx is 1/2 secant x tangent x plus 1/2 ln of secant x plus tangent x plus some constant c, and that's our solution. We haven't even thought about 7.3 yet, guys. How are you feeling?
It's all right. I think once I do homework, you get a couple under the belt,
All right,
or like
good.
a couple hundred, I'll get it.
All right, good, good. All right. This is a problem that I embed in an exam also. It's a good problem. And eventually you get to the point where you're like, I don't want to know the process. I know the answer is 1/2 secant x tangent x plus 1/2 the ln of secant x plus tangent x plus c. You're like, I'm not doing all that work. Yeah, sometimes it's like, okay, the work doesn't justify getting the answer, so I'm just going to remember the answer. So, unfortunately, on a test, if I put it on there, I'm going to look for the work, right? Okay. Some trig that you need to know. If we have problems that are sine of some number times x times cosine of some other number times x dx, when we're integrating, we need to know how to break those up. And so to break those up, we need to know this trig. So this is something that's going to be important for you guys to know and to memorize, or if you're not going to memorize it, have it written down on a sheet of paper when you take my exam. Okay, that's going to be something that's going to be quite important to do and use. So I'll give you guys a second if you guys want to write down these before I do an example.
It's a good thing to have it memorized, though, right, for future math courses?
Yeah, I mean, it is, but if you have a quick reference, if you know what you're doing and have the quick reference, it's good. There's just so much you can memorize. At some point, you're like, dear Lord, I'd rather have it on a piece of paper where I can refer to it and be 100% correct, as to trying to rely on my brain and being like, I think that's right. But it's useful. Okay. Dear Lord. All right, can I do the last example for this section?
Yeah.
All right. And I'm going to be using these rules. So here we go. So in this example here, it's sine 4x cosine 5x. So which one is that form? A, B, or C?
A.
It's A. So then that tells me, and I'm going to write it down here, so when I use it, you guys can see it. Here we go. So I'm going to change my integral using that rule, because it'll make things easier for me. Because what I'm going to do is, this is a product that I don't know what to do with, so I want to break the product up into some sum. So what's going to happen is I'm going to get the integral of sine of, let's not forget the 1/2 out in front, A, which is 4x, minus B, which is 5x, plus sine of 4x plus 5x. Right? This whole thing times dx. Are we in agreement?
Yep.
Okay. So then what this is going to be is 1/2 the integral of sine of negative x plus sine of 9x dx. And then we know something about sine of negative x, don't we? Since it's an odd function, isn't sine of negative x the same as negative sine of x? Do you guys
Yep.
agree? Okay, so then I'm going to write this as two integrals. So this is going to be a negative 1/2 integral sine of x dx plus 1/2 integral of sine of 9x dx. And so when I take the integral of each, I'm going to get the integral of sine is negative cosine, right? Plus some constant plus 1/2 times 1/9 negative cosine of 9x plus some other constant. And so what I'm going to get is 1/2 cosine of x plus, I should put minus 1/18 cosine of 9x plus some new big constant. Are we all right?
Yeah.
Yeah.
Okay. All right. That is 7-2. It's a chunk of work. I'd recommend that you guys probably watch the video again at some point, just because there is some amount of work to this. Okay. All right. Let me go on to 7-3. And we'll go from there. Okay, something cool is this is a table that's going to be a reference for you on when to use what. So one of the things that's important is if we have something in the form ax squared minus x squared, we're going to use this as our substitution. Okay, x is equal to a theta. If we have a squared plus x squared, then we're going to use x is a tangent theta. And then if we have x squared first minus the a squared, then we're going to use a secant theta to be able to manipulate these problems. All right? Those three substitutions will be imperative. Please know how to use them. This integration here takes some work and some thought, and then you need to be able to know how to use triangles. So we're going to be building triangles, and I'm going to show you how to build those triangles, okay? So this is fun. It's actually really, really cool. I enjoy it. I hope you do too. So when we look at this first problem here, we're looking at the roots, right? So this root here falls under which one? The first, the second, or the third?
The first.
It falls under the first, right? Because my 9 is a squared minus x squared, so it's that form. So it tells me that I should use this x is equal to a sine theta. So then x is going to be equal to a. It's the root of 9, so that is 3 sine of theta. Okay? We're going to take the derivative of this, but before we take the derivative of it, I want to be able to go get I want to be able to draw the triangle that I'm going to need. So the triangle that I'm going to need is going to be a right triangle, right? And this is going to be my theta. And the way that I'm going to think about this is x equals 3 sine theta is the same as sine theta is equal to x over 3. Do you guys agree?
Agree.
Okay. And sine, we know from trig, is the opposite over the hypotenuse, right? So the opposite would be x. The hypotenuse should be 3. And then the adjacent side would be 9 minus x squared rooted. Does everyone understand how I developed my triangle?
Yes.
Okay, cool. So then, now from here, what I'm going to do is I'm going to do some substitution, but before I do the substitution, I'm going to take the derivative of what I'm substituting for. So this is going to become dx is 3 cosine theta d theta. Sorry, I had to move something. So when I go to do the substitution, I'm going to go the integral of 9 minus 9 sine theta squared under the root over 3 sine theta squared. And then dx really is 3 cosine theta d theta. Does everyone agree with the substitution that I've done?
Yes.
We're okay? Okay. So then in manipulating this, oh, I'm sorry, this should be a 3. My bad. That should be a 3. So what we end up getting is the integral of 9 minus 9 sine squared theta under the root over 9 sine squared theta times 3 cosine theta d theta. Bringing out the 9 and the root, that's going to become a 3. Root 1 minus sine squared theta times 3 cosine theta over 9 sine squared theta d theta. I'm trying to show you all the work. I don't want to skip steps. 1 minus sine squared theta is what? Isn't that cosine squared theta?
Yes.
And the square root of cosine squared theta is cosine theta. So I should end up with 3 cosine theta times 3 cosine theta all over 9 sine squared theta d theta, which the 9's cancel, and I'm going to get cosine squared theta over sine squared theta d theta. And cosine squared theta over sine squared theta is what? Isn't that cotangent squared theta d theta?
Yep.
Okay. And now this step is remembering your integration for cosine squared theta. The integration for cosine squared theta is cosecant squared theta minus 1. Right? When we're going to break it up, d theta integrated. And the cosecant squared, the integral of cosecant squared is a negative cotangent theta. The integral of 1 is theta, and then we have to add some constant c, correct? Are we in agreement?
Yes.
Okay. Now we're going to go back and play with the triangle. So, remember we had sine theta was equal to x over 3. I need to find out what theta is, right? So theta, isn't theta going to be sine inverse of x divided by 3?
Yes.
Okay, good. So now I know what theta is. What's cotangent? So I'm going to bring this up here just so we can have it. Cotangent is, instead of the opposite over the adjacent, it's the adjacent over the opposite, correct?
Correct.
And we're looking at the triangle. So what we had is negative, I'll write it, negative cotangent theta minus theta plus some constant c was our solution. So minus adjacent over opposite is going to be square root of 9 minus x squared over x. That's cotangent. Our theta is sine inverse of x over 3 plus c. That's our solution. So we need to be able to, in these problems, understand the triangle, understand our trig integration, and then be able to substitute all back in. Because since our problem was an integration in terms of x, our answer needs to be in terms of x.
Pretty cool.
I'll give you guys a second. I'm sure right now you guys are like, Lord, Lord. Trying to get as much of it for you to see as possible. Are we okay?
Yeah.
May I move on to the next problem?
Yeah.
There's no questions on the process that I've done so far?
Makes sense.
Okay. All right. So let's go to the next one. So again, we're going to look at the root. And in this case, we have the x squared first with a plus the a squared. Which one had that substitution? Which
I think
one?
it was C.
So it was x squared plus a squared, right? So if we go back up just so we can see, isn't it the second one?
Yeah.
With the tangent,
Oh, yeah, second one, sorry.
right? So the substitution for this one should be x is equal to a tangent theta. All right, that's important. So understanding the substitution, right, and seeing what it looks like is important. So in this problem, if that's our x, then we're going to go x is equal to 2 tangent theta. Agreed?
Agreed.
Dx is going to be 2. The derivative of tangent theta is secant squared theta, d theta, right? Okay.
Yeah. Yeah.
And then when we try to draw our triangle, we're going to go tangent theta is equal to x over 2. So the triangle that we're going to build, here's our theta. It's opposite over adjacent, so that's x, that's 2. And this would be x squared plus 4. Notice that if we draw our triangle correctly, we end up with the substitution. We end up with the rooted substitution that we decided which one to use. Does that make sense? So this ends up being the thing that helped us decide what we use to substitute with. Does that make sense? It shows up in our triangle. Okay. So now let's do the substitution. So I'm going to get 1 over, here's my integral, of 2 tangent theta squared root of 2 tangent theta squared plus 4 times 2 secant squared theta d theta. Are we okay?
Yes.
just so you guys see, this represents this. This represents this. And then this is represented here. So everything is there for us. Okay? Just trying to make sure that you guys see everything is in there. All right, so then the integral is going to go 1 over 4 tangent squared theta. In the root, well, I'll show it. I was going to be lazy. But I can't be lazy. Because me being lazy hurts you guys. So then I can pull a 4, I can pull the square root of 4 out, so that's going to cancel the 2's, and so I'm going to get 1 over 4 tangent squared theta. Tangent squared plus 1 is secant squared, which is going to become secant theta times 2 secant squared theta d theta. We can see that we can cancel out some things, and so we're going to get, I'll pull the 1/2 out finally. Ooh, that's funny, I canceled out the 2 but didn't cancel out the 2. Here. I'm going to get secant theta over tangent squared theta d theta. Are we okay with that? Does everyone see how?
Yes.
Does everyone see how this 2 got eliminated with the 2 that got eliminated from here?
Yes.
Okay. To make my life easy, I'm going to do everything in terms of sine, because sine, cosine. Hopefully it helps you guys to be able to see it. So that's 1 over cosine theta over cosine theta over sine theta d theta, which is going to become 1/2 integral of sine theta over cosine theta squared d theta. Ooh, actually I messed up. Huh? That's funny. The bottom's squared, so this should be squared. This should be squared. So what ends up happening is I'm going to get I flipped it before I even I was thinking 2 steps ahead. So when I multiply by the reciprocal, I'm going to get cosine theta over sine squared theta d theta. Does anyone need me to show how I got that?
Can you show it?
Sure. So what ends up happening is, and I'll do it over here in a different color, I get 1 over cosine theta over tangent squared is sine squared theta over cosine squared theta, correct? So when you divide by a fraction, you're going to go 1 over cosine theta times the reciprocal. The cosines are going to cancel, and so I'm going to have a cosine on top and a sine squared in the denominator. And that is this piece right here. Is that okay?
Yeah, thank you.
Mm-hmm. Let me know when I can erase it. I need the space, unfortunately.
Right, I got it, thanks.
Okay. I'll erase it. All right. So then from here, this problem, I'm going to bring it up here. I want to use the space. I'm going to let u be sine theta, so then du is going to be cosine theta d theta, which takes the numerator. So I'm going to get 1/2 the integral of 1 over u squared du, and that's going to be a negative 1 over u plus some c multiplied, which is going to give me 1/2, a negative 1/2 times 1 over sine of u plus some constant c, which is the same as a negative 1/2 cosecant theta plus c. And now we got to look at our triangle, right? So the triangle, cosecant is, sine is opposite over hypotenuse. So now cosecant is hypotenuse over opposite, correct? So then opposite or hypotenuse is this. So I'm going to get a negative 1/2 times root of x squared plus x over the opposite, and the opposite is x, correct? Plus some constant c. So just to clean it, I'm going to get negative radical x squared plus 4 over 2x plus some c. Does everyone understand how I got these values for cosecant? It's okay if you don't. I'm willing to go back to the trig to explain it. You could even ask privately. No one would know. No, we're okay?
Yeah, I get it.
Okay. So to get from here to here, I got to go back to some trig. And in the trig, remember, the thing that you were taught by your teachers was this, right? So sine is opposite over hypotenuse, correct? So sine is opposite over hypotenuse. Cosecant is the reciprocal of that, so it's hypotenuse over opposite. And so this is the triangle that we're looking at. This is the angle, so that's opposite, that's adjacent, that's hypotenuse, right? So we said it was cosecant, so it's hypotenuse, which is x, the square root of x squared plus 4, over the opposite. So when I'm here, this is that value in terms of the triangle. So this cosecant theta gives us this. Does that help?
Yes.
Okay. Just remember this. This is a good reference to have for your trig when you're looking at triangles. Okay? That should really help in breaking these all down, because we're going to be using it so very much. Okay? Does everyone have this one written down?
Yes.
Okay. All right, on to the next. So we have, and I'll just rewrite it so we have a little bit more space. It's integral of x over the root of x squared plus 4 dx, and we can see this one is also going to be the tangent substitution, correct? So in this one's case, x is going to be equal to 2 tangent of theta. Agreed?
Agree.
So the triangle that we have again is the same triangle that we had in the previous problem, which is going to be opposite over adjacent, and this is going to become x squared plus 4u. So that's the triangle that we're going to have. Again, it's the same triangle. So then when we do the substitution here, I should get the integral of 2 tangent theta over 2 tangent theta plus 4, this quantity will be squared, times, and I need the dx, right? So the dx is going to be 2, and it should be secant squared theta d theta, which will give me 2 secant squared theta d theta. That's a big deal. Okay? Now, does this look like it's very pretty? Does
Nope.
it look like it's going to be a lot of fun work? When we go to clean it up, and I'll just show you, it's going to be 2 tan theta, 2 secant squared theta over, now the denominator, I'll be able to pull out a 2, correct? And then I should get the square root of secant squared. Do you guys agree with that, or did I skip too many steps? It's okay if you think
I agree with.
Is there anyone who thinks I skipped too many steps? It's okay. Nobody? Okay. So then what's going to happen is I'm going to have a 2 out front. I'm going to have tangent theta, and then secant theta, d theta, because the secant in the denominator is going to cancel with the secant squared, correct? Do you guys agree? Okay. Now from here what ends up happening is we could do this in terms of sine and cosine and attack this problem, which I'll show you. It ends up being sine theta over cosine squared theta d theta. Agreed?
Agree.
Okay. And then my u substitution is going to be cosine theta. So I'm going to get du is negative sine theta d theta. And so this is going to be negative 2 integral of 1 over u squared d theta, which we know is going to be 2 times 1 over u. And then when we substitute, plus some constant c, when we substitute, we're going to get 2 over cosine theta plus c, which is the same as 2 secant theta plus c, and then we got to go look at the triangle, right? And secant is the reciprocal of cosine, so it's adjacent over hypotenuse, which means this would be hypotenuse over adjacent, right? So what that's going to give me is 2 times hypotenuse, which is x squared plus 4, over 2 plus c, which ends up giving me radical x squared plus 4 plus some constant c. Does that make sense?
Yes.
Okay. Or, well, I'll let you guys write it down. Tell me when you're ready, because I'm about to make you guys very upset.
Okay, I'm ready.
Okay. Or, this is so cool, going back to that original problem, I could have seen something cool. I could have just gone u is x squared plus 4, du is 2x dx, 1 half du is x dx. The numerator is gone. Integral of 1 half 1 over u to the 1 half power du. Right? And when we do this problem, we end up with did I get that right? Okay. That's going to be 1 half u to the negative 1 half power. When I integrate that du, I'm going to get u to the 1 half power multiplying by the reciprocal gets rid of the 1 half plus some constant c. What was my u? X squared plus 4 plus some constant c. Trig substitution will work, but if there's an easier method, use the easier method. Make your life easy. Now, will you guys be honest with me real quick? How many of you in here are feeling like, oh man, I don't remember my integration? Anybody? You guys feel comfortable with it?
Me.
Yeah. So as you're going through this, be gracious with each other. Be gracious with yourself. This is going to take some time, you know, especially for those of you who took the class in the spring. It's a jump, right? And so you're going to have to practice your integrals and your derivatives. And so I fully figure that next Wednesday when we meet, all I'm going to be getting from you guys is, how do I do this problem? And so I'll be doing a lot of problems for you guys, but it's cool. That's okay. Be gracious with yourself. It's going to take some time. This is probably going to cause a little bit of stress, but just work through it. And as you need help with integrations, please shoot me an email. All right. I want to make sure you guys are comfortable with this. And then part of the thing's a bummer is when you see problems like this one, the easy method is like 2 steps. The trig method is a bunch of steps. It's not about getting to the right answer. It's about being efficient when you get to the right answer. So understanding your techniques of integration becomes so very important. Okay? All right, let me show you guys one more example. And then we can go into me answering questions or explaining something that you might not understand. All right, so here's our next problem. So this problem, is it in any of the 3 forms that I've shown you so far? It should be fairly obvious that it's not, right? It's not in the form of a squared plus x squared or x squared plus a squared or a squared minus x squared. It's not in any of those 3 forms. And so since it's not in any of those 3 forms, we need to do some manipulation in this problem, obviously. And so the one thing that we're going to do is we're going to take that denominator and we need to put it in the form either of a squared minus x squared plus x squared plus a squared. I'm trying to remember all 3 of them. We're going to have to manipulate to put it in that form. So what I'm going to do is I'm going to look at what's in the radical and manipulate it. So I'm going to go 3 minus 2x minus x squared. And then what I'm going to do is I'm going to go 3 minus, and I'm going to go x squared minus 2x. And now what I'm going to do is I'm going to complete the square. Okay, so I'm going to go 3 minus x squared minus 2x. And then in order to complete the square, I need to take half of 2, which is a negative 1, and then square it. So negative 1 squared tells me to add 1 here, right? But am I really adding 1? I'm actually subtracting 1 because of the sign in front of the parentheses, correct? And since I'm doing that, to keep balance, I need to add 1 on the outside. What this then will give me is 4 minus x squared minus 2x plus 1, which will be 4 minus x minus 1 squared. Ooh, I messed up. This should be a plus. Plus, plus, plus. No one pointed that out. Terrible. Are we okay? Okay.
Yes.
So then from here, what form is this in? Doesn't this look like a squared minus x squared? Right, the parentheses is the x squared piece.
Yes.
If you aren't comfortable with that, what we can do is we can do this. I'll go u is x plus 1. And so the way I'm going to rewrite it is the integral is going to be u minus 1 over 4 minus u squared rooted du. Do you guys agree? Because du is dx.
Yes, I agree.
You guys agree this is this? I'm just trying to make
Yes.
it so it's in the form that something that you can all see. Okay, so then I'm gonna, now that I have this integral, I have to do a trig sum to this. And what's in the form of a squared minus u squared? Or a squared minus x squared, what's in that form? What was the substitution? Wasn't it, we'll let u equal 2 sine theta? Right? Isn't it sine theta that we use here?
Yeah.
So then du, it's funny, I don't like using u again, but it is. It's a different du. I'm going to get 2 cosine theta d theta. Okay. And then from here, I'm going to rewrite this as 2 sine theta minus 1 over the root of 4 minus 2 sine theta squared times 2 cosine theta d theta. that will become 2 sine theta minus 1, 2 cosine theta over square root of 4 minus 4 sine squared theta theta, which will be 2 sine theta minus 1 times 2 cosine theta, bringing out a 2, 1 minus sine squared theta d theta will be 2 sine theta minus 1, 2 cosine theta over 2, that's going to be cosine squared theta, which becomes cosine theta d theta, and so I'm going to get 2 sine theta minus 1 over, oops, no over, they're done, that's awesome, d theta. Does that make sense?
Yes.
Okay, which will then be a negative 2 cosine theta minus theta plus some c, and now I need to manipulate this thing. Okay, and here's the important piece. My triangle that I made was in terms of u's, right?
Right.
And so, what was it that I used? I just said, so u was 2 sine theta, so u over 2 is sine theta. So opposite is u, hypotenuse is 2. This should be 4 minus u squared, square root. Agreed?
Agreed.
Okay. One of the things that's important too is we need to know that u, or u was x plus 1 originally. Right?
Right.
Okay. So, I'm going to rewrite the triangle so that it has the right information when I substitute. So I'm going to have 2 x plus 1, 4 minus x plus 1 squared. But guess what this square root is down below? When I simplify that, it's going to be 3 minus 2x minus x squared. See how we're going back to our original problem? So from here, I'm going to have a negative 2. Cosine theta is adjacent over hypotenuse, correct? Okay, so adjacent is going to be square root of 3 minus 2x minus x squared over 2, right? Minus, we need to know theta. And so theta would have come from here. So I've got to manipulate this. I'm going to get sine inverse of u over 2 is theta. But isn't that sine inverse of x plus 1 over 2 is my theta? Correct?
Correct.
I'm tired. I can imagine what you guys are feeling. Is there any question on this problem?
For the 2 and the negative 2 and the numerator and denominator, will we have to simplify that?
Yeah, it would clean up to eventually be this.
Oh,
Right? That would eventually clean up and our finished product answer. mean, this one's probably better, right? Ah, shoot. It hurt my eyes when it was squiggly, sorry. All right, are there any questions on this problem at all?
I was just wondering how you got the 2 sign for the U.
2 sign for the U. Oh,
When you did the second U substitution.
okay, so how I got this piece?
Yeah, like where'd you get that from?
From the beginning. So from up here. So when I had this problem right here, right? This problem, this is in the form of the substitution that I talked about at the beginning of the class that stated that a squared minus x squared, the substitution that you want to use for that is x is equal to a sine theta. So my a is 2.
Okay, that makes sense.
Did you see that? Are we okay? I'll post this video up today. I have to go to the dentist right after this, so unfortunately I won't have an office hour right after this class, but I will make myself available for you guys sometime before, well, my office hours I'll have tomorrow and on Tuesday to be able to answer any questions you guys might have on any of this material. I didn't give you a lot of homework. I think I gave you 7 and 9 problems on these 2 assignments, and you have a full week to do them. Okay?
Okay.
All right, I'll stop recording and then I'll answer any questions you guys might have about other stuff. I just don't want this video to be too crazy long.